and welcome to the Physics Colloquium. Today we have Dr. Michael Zemcov from Caltech. Michael went to college, University of British Columbia, Vancouver, so he's not a stranger to snow. And subsequently earned his PhD at Cardiff University in the United Kingdom, studying the polarization of the cosmic microwave background radiation. Subsequently, he was a postdoc postdoctoral fellow at Jet Propulsion Lab, and currently he is at Caltech, senior postdoctoral fellow, applying innovative detector technology and data analysis methods to perform precision cosmological observations. Today he will speak to us about a large-scale structure of the cosmos.
Thank you. Thanks for inviting me to speak. I'm excited to talk to you, and I realize that the time constraints in the room are limited, so I'm going to have to fly through my slides. So just let me give a little introduction, in addition to what Mishkat just said. I worked initially in CMB, doing my PhD, doing CMB polarization measurements. And then when it came time to do my postdoc, I went to Jet Propulsion Lab. And it became apparent to me that CMB was a situation with too many cooks and not enough pot. So I decided to use the same techniques but applied to different wavelengths to do different kinds of science. So in that time, I've been at Caltech for quite a while now. Your research portfolio grows, so this is kind of a potted list of the things I consider myself expert in. And if I told you about all of them, we'd be here for 3 hours. So I'm going to have to reduce it down to just the first two here. So the talk today is about this relatively new method called intensity mapping, which we're using to measure the large-scale structure of the universe. And I'll try and tie that in with detector development and optimization because these two concepts are very intimately tied together. So just a brief outline so you know where you are. Let's talk about cosmology for a few slides so you know what it is that I'm interested in doing and how we do it. And then I'm going to introduce you to this method of intensity mapping, just because it's not something people think about very much. And I'm going to tell you a few recent results that I led using this method, namely Cyber and Herschel Spire, and then some future opportunities that I'm heavily involved with in leadership roles that are interesting. Okay, so let's review cosmology as we currently understand it. This is the work of 100 years or more trying to map the large-scale structure of the universe at all wavelengths to really understand how things fit together. The picture we find ourselves with is a Big Bang at some point in the past, 13.6 billion years ago, followed by immediately by what we call the epoch of inflation, which is the idea that the Big Bang is this hot, very extremely dense event that basically expands, that has quantum fluctuations within it. And these quantum fluctuations need some mechanism to expand to cosmological scales so we can explain features of the universe we find around us today. And that mechanism is called inflation, and the idea is there's some field in the early universe that causes many e-fold scale increase from tiny sizes to large sizes to explain how do we get an isotropic universe that's still seeded with inhomogeneities so that we can form stars and galaxies. It isn't perfectly uniform. After that, it's a kind of particle soup where you basically have subatomic particles banging into each other and over time cooling down and coalescing to form larger and larger structures like nucleons. The first observable thing in the universe is the cosmic microwave background, and that's about 400,000 years after the Big Bang. And that is when protons and electrons form neutral hydrogen, thereby releasing photons. And the universe had cooled at that point to such a state that those photons can now travel without interacting with the neutral medium anymore. So this is now redshifted into it was emitted in sort of optical wavelengths, but is now redshifted into the millimeter, and this is the surface of last scattering that we study to understand the infant universe. After that, we have what we call the cosmological dark ages, when everything's basically neutral hydrogen, a little bit of helium, and photons just banging around in the universe, and of course dark matter. Banging around in the universe, not doing a whole heck of a lot except falling together under gravity to produce larger and larger structures. And about 0.4 billion years years after the Big Bang, we start to get the first stars. So these things streaming down, which we'll talk about in the next slide, are forming stars and eventually galaxies. Those galaxies are a lot different than the ones we see around us today in a way that we don't quite understand. So there's a huge industry in astrophysics of understanding this evolution of galaxies from early things to things we see around us in the universe. And then finally, here we are now building spacecraft and other instruments to try and understand this whole picture. So large-scale structure is basically we study it to understand how do we go from this hot, dense soup in the early universe to stars and planets in you and me. That's the real question here. And these are the biggest questions we can ask. So this is a simulation where in the upper corner, this is now time after the Big Bang in giga-years. And this is roughly the distance between us and the Andromeda Galaxy. So this is, cosmologically speaking, not a very big scale. And you can see here the picture we formed. This is using our modern understanding of the physics, where the purple is dark matter, and the yellow are baryons, so the things that make up stars and planets and so on. And the picture you have basically is one where these things are gravitationally attracted to one another, and eventually you reach a critical density where baryons can start forming stars and galaxies, and then things get a little bit messy because baryons are messy and bang into each other in complicated ways. But basically, everything's streaming together along these filaments and starting to form more and more massive structures as time goes on. So that's the general picture, and that's been the work of generations. And it actually is remarkably cohesive. It's resulted in what we call concordance cosmology. It's kind of agreement about what the truth is. But there's many missing pieces to this puzzle, or at least things we don't understand in many ways very profoundly. One of the most critical is the question of the mass and energy density budget of the universe. So, equals mc squared, mass and energy. We really want to know what the energetic components are in the universe. And we find ourselves in a strange situation where 70% of the universe is made of what we call dark energy, which is something we hardly know anything about. It was discovered by trying to understand the distances to supernovae and noticing that the further away they are, the more they're accelerating from us. And it behaves like a kind of anti-gravity, like a pressure, which is a very strange thing. So we're in this funny situation where the universe is actually accelerating in its expansion now. And that's due to this stuff. The 25% piece of the pie here is dark matter, which this cartoon is about. So visible matter is made of protons and photons and even neutrinos, things like that. Dark matter, we don't really know what it is. We have some very good guesses what it might be. These things compete for our attention. We haven't detected it directly, so we don't really know what particular species is responsible. We do know, how it practically affects large-scale structure, which is it acts like a sort of gravitational particle that doesn't interact via other processes, so it really enhances gravity and makes galaxies look more massive than they actually are. And then even the minor slice here, which is the sort of visible matter we find ourselves with in the universe, we don't really have a good accounting for that budget, and I'll go into that a little bit. The question there is how much of the matter in the universe is in stars, how much is in gas, how much is in the ionized phase. And when we add up those components using different measurements, we don't get to one. There's still missing matter in the universe, and this is a big puzzle right now. Another topic that large-scale structure addresses necessarily, of course, is the formation of structure. So the question here is one of galaxy formation and how do galaxies evolve over time. In the recent universe, we have a pretty good understanding of that. But going back to the distant universe, and more specifically this reionization epoch, which is addressed in this movie, you can see here the neutral medium in black, and then the first stars are in the center of these bubbles, producing ionizing fronts in red, and blue is the ionized phase. And you can see what's happening is that you start out with this thick fog, where you're forming these ultraviolet bright stars. They start burning holes in it, getting rid of the neutral medium, and eventually at the end of this movie, you see a universe like we find ourselves in today. This process, this is a simulation, of course, this process is not well understood, and we're just starting to get there observationally to be able to understand it. So there's a lot of questions associated. What's the history of star formation in the universe? Finally, for me, it's a good day when I get to do this kind of stuff is the fundamental physics aspect. So the way we discovered dark matter and dark energy was by understanding large-scale structure and where galaxies are in the cosmic web. Right? That remains the case. These things are small effects, and in the laboratory setting are impossible to measure. So what we really need to do to understand them is to understand how galaxies are affected by them, and thereby infer properties of what these fundamental fields must be. And then finally, physics beyond the standard model, meaning inflation. Inflation imparts some kind of structure to where galaxies are seated in the large-scale structure. And so by measuring that very well, we can understand that and also other physics beyond the standard model. So this is really the frontier of what's interesting and cool about large-scale structure. So let's now talk a little bit about intensity mapping quickly. So the question is, how can we measure large-scale structure? Here's a cartoon. This is what the cosmic web looks like, according to an artist. And I've circled here knots where in a shallow survey of this field, you might say that's a point source. That's a galaxy or whatever that I'm going to detect. I'm going to use those to trace this web. And that's what people do, and they've been doing that for 100 years, and we're getting very good at it. So you can go out and you can do such a survey. So this is the Sloan Digital Sky Survey. And in fact, there's more recent ones that have less photogenic plots. You can see here the cosmic web being begun to trace out. This is 10 to the 5 galaxies out to 1.5 billion light years from us. So you can really start to see this large-scale structure in such surveys. But there's a second way that's kind of less known, which is to say, okay, I don't care about point sources. I'm not going to go out and I'm going to try to detect them individually because that's hard. What I'm going to do is I'm going to only look in broad regions. So I've taken that same image and I've kind of smoothed it with a broad kernel. And then what you do is you measure statistics. So you ask, how does this region compare to this region? How does this region compare to this region? Measure the statistics in your image and compare that to models to infer what must be the background that's producing such an image. We call this intensity mapping. And just to introduce, because I'll be throwing a few up, the way we tend to talk about that is in terms of angular power spectra. So that means you take this kind of image, you compute its Fourier transform, square that, and then do an angular average, because in cosmology we don't care about phase, there's no information carried there. And basically, big Fourier modes in the sky map to low wave numbers, and then on up. So you're marching up in wave numbers here with some amplitude. And just to make that a little easier to unpack, here's a picture, a little movie going by. So this is the cosmic microwave background temperature spectrum as it happens, showing you large Fourier modes and then marching up to smaller Fourier modes. So the information in this image, or at least the sum of all these images, is encapsulated in that kind of plot. So this is the statistics we're trying to measure. Okay, so going out and measuring point sources seems on the face of it pretty easy, right? You just go do that. It's like measuring stars. So there must, if I'm talking to you today about intensity mapping, there must be something interesting about it. It offers significant advantages in three basic situations. One, when sources are difficult to detect, and that could be because you have an instrument with a big beam necessarily. So this is Herschel Spire, which is a submillimeter telescope I'll tell you a little bit more about. And a feature of it is that it's working in the submillimeter with a single aperture, so it doesn't have very good angular resolution. There's in fact no actual instrument noise, or virtually no instrument noise in this image. This is all confused sources on the sky in 3 colors. So you might pick out individual sources and say, yeah, okay, well I can measure some of those sources. But in the statistics of this image, there's a huge amount of information that's just lost. The second and even more interesting situation you can find yourself in, cosmologically speaking, is when the source population you're interested in is very faint. So if you say, okay, well, I could detect those as individual sources, but it's going to take a gajillion years on a big telescope, that's not very compelling, where if there's a lot of photons, because there's a lot of these faint sources, I can go out and I can do an intensity map and tell you what's going on in that image. Another situation that's good for intensity mapping is when you require the total emission. So to cartoon this is again a spire, but this is a catalog simulation. This is bright sources that you detect as individual things. And this is all of the sources that exist in the universe, or at least a simulation of them. And you can see that just by detecting the bright guys, I'm missing the whole picture here. And that's because there's a lot of photons wrapped up in little faint things that are confused and roughly equally bright. So really to get the whole picture, we need to understand these faint things. And finally, you can find yourself in a situation where the emission is truly diffuse, like the cosmic microwave background. That's not resolvable into point sources. That has to be some kind of intensity mapping. Okay, so probably everybody in this room is aware that we go out and we map positions of galaxies, because we've been doing it forever and we're getting pretty good at it. But you probably haven't heard of intensity mapping. Why? The basic reason is that to do intensity mapping, like I said, we need to be doing Fourier transforms of images, which means we need to understand the Fourier components in those images very well. What that means is we need really high fidelity images of the sky, or at least to understand how they're corrupted. So what's come on the scene in the past 5-10 years that wasn't really available before is a new generation of detectors on sensitive survey instruments that have allowed us to make these really high fidelity images of the sky and trust that when we make a measurement, that's the actual sky on all angular scales in the image. So this has really been a technological problem, not one of conceptual nature. So this is really a wave that's just beginning to crest, and we're starting to see some real interesting results come out of it. And I think over the next decade or two, we'll have some really compelling stuff happening. This is really a good way to get at faint populations. The other advantage, and this is very interesting, that it has is because I'm not really looking at point sources, I don't need a ginormous telescope. But once you remove that restriction, life becomes really easy because telescopes in astrophysics are really what drives cost. So I can go out and I can do really good science on modestly sized aperture telescopes. And as a case in point, this is an experiment we did in Table Mountain in the back of JPL last year that we're putting a paper out now that was actually led by a student of mine. And this is just the piggyback telescope. That was the telescope that has a mount, and we didn't use it at all. What we did was we put our telescope on the side. So this is our telescope, and that's a cryostat with a detector in it. And we were able to do really good science with that. And we built this out of spare parts in my lab. So this is really compelling stuff you don't need to have a Keck or a Gemini for. Also, because I don't need those big telescopes, it's really short design to deploy times. What you do is you say, give me your detector, give me your detector. I can make optics and get it on something like this, say, very quickly, relatively. You know, big telescopes have 10, 20 years development times. This you can make in months. So if you say, I have a great new detector, it's really good, you can get it on the sky doing stuff relatively quickly. You don't have to wait for an instrument cycle. And finally, because it's a young field, it's one of those ones where phase space hasn't been collapsed and every niche isn't occupied right now. You can do useful measurements with both broadband and spectrometric instruments. It's really kind of the Wild West out here. We can do a lot of different things, and it's very intellectually stimulating that way. Okay, so let's talk about some recent results real quick. Let me unpack reionization very quickly. So this is a prime candidate for intensity mapping, like I said, because the sources that did it are very faint. So what people do now is they get big telescopes like HST, and they use a dropout method where you see it in long wavelength bands, but you don't see it in short wavelength bands. And you go and you try and find sources that are just long wavelength detected. And you say, okay, well, I know what wavelength that filter set corresponded to, so I know what redshift, how far they are from us. So you can find stuff at redshift 7, 8, which is sort of at the end of this epoch of reionization we're trying to study. And you can start building up luminosity functions. So this is basically the brightness, the intrinsic brightness of a source, and then how many you measure. This is kind of the name of the game here, at least right now. So at redshift 4, when you're not doing reionization, you can do really well. But as you march up to redshift 8, when the action's happening, you're not doing so well, and you really haven't detected a lot of sources. They're very hard to find. In fact, JWST, which is an example of a huge, expensive, monolithic project, if you look, these are luminosity functions again, and we're marching up in redshift 5, 6, 7, 8, 9, 10. 10 is sort of the beginning of the process, or at least the first third, which is really exciting to understand. Hubble with WIPIC 3 is detecting down here, JWST can do there, so at redshift 5 you're fine, but by redshift 7, HST is only getting 20% of the sources, JWST is getting 50, and as you go up to redshift 10, even JWST is only getting 18% of the sources. So we're not seeing these sources. They're really hard to detect. They're very faint, very diffuse, very distant. So what do? Well, we have this method called intensity mapping. So I told you that what we're interested in is the ultraviolet emission, which of course, because it gets redshifted as 1 plus c, gets redshifted to the near-infrared today. So we're talking about building a near-infrared telescope. So what do you need to do this kind of experiment? You need a large area. So this is a simulation at redshift 7.3. It's 180 megaparsecs on a side, which isn't very useful. So it's 1.2 degrees. So this is a few full moons worth of sky. And on here, I've put the Hubble ultra deep field. So this is this deep stare that Hubble does. And you can see this is its size, and it's not a fair statistical sample. It's not even close to a fair statistical sample of this distribution. So we need some big, large area if we're going to ask, what are the statistics of this process? Can I model it? Atmospheric emission is a problem and from the ground, so you need to get either above the atmosphere or mitigate it some other way. It's 1 million times brighter than the thing we're looking for, so it's a problem. And finally, you need a couple bands because you're looking for a spectral feature here to tell you what's the low redshift stuff, what's the high redshift stuff, so you can do a comparison experiment. So I don't know about you, but I look at that and I think, well, gee, if I could get in space with a multi-wavelength wide-field camera, I could do this, because there's a lot of photons there to detect.
I don't want to take up much of your time, but
Yep.
a moment ago you said short deploy times and cheap, and now you said space, and so now I'm beginning to cognitive dissonance.
That is a great segue to this slide. So we went and built that on a sounding rocket experiment. So that's where I get my cheap and quick from. So this is the cosmic infrared background experiment. This is built to answer this kind of question exactly. We call it CYBER. It has actually 3 instruments, 3 different science projects on board that we're responsible for. There's 2 spectrometers. I'll tell you about offline if you're interested. I won't tell you now. But there are 2 fluctuation cameras on here. One's tuned to 1.1 microns to measure this low redshift signal, and it's 2 by 2 degree field of view. And one at 1.6, same area, that's tuned to the reionization signals. So we have these 2 cameras, wide field, that we can go out and do this kind of measurement with. So sounding rockets are kind of fun. This is a student, Ian Sullivan and Koji Samura, that have since moved on to be staff and faculty members, it happens. This is the telescopes, and that's a liquid nitrogen cryostat. This whole thing is cooled to 77 Kelvin. So once you've spent years building it and characterizing it and understanding it, you have to integrate it with the rocket. So this is a rocket basically flayed out on the table. Here's CYBER in this can here. The skin is also the vacuum jacket, the rocket skin. That's the telemetry section, so we live telemeter data down. This is the attitude control system, so that controls where we're pointed on the sky. And then finally, a parachute to recover the payload. And once you've done all that, you can put it on a rocket. So that's the payload up there. And then there's 1, 2, 3, 4 motors on this one. This is a big one. And the really nice thing about sounding rockets as opposed to real NASA projects is on a NASA project, you build it, and you give it to NASA, and they go away for 6 months or a year, and they say, oh, yeah, okay, we're going to launch it in a week, right? You're not involved in that process very much. Sounding rockets, this is myself, this is a grad student, out on the pad, working on the payload, getting ready for flight. So you get to be there. It's really cool. So, of course, once you've built it up, you get to fly it. So these sounding rockets are basically military ordnance. They're ICBM missile interceptors. They go like a bat out of hell. You get about 7 minutes of data in flight, and you get 5, 6, 7 fields worth of data in that time. And we do multiple flights so we can check against, time of year, that sort of thing. There it goes. So once you get your data, which is, again, live streamed down, it looks roughly like this. This is actually cropped. The image is bigger, but here's the full moon just to show that it's a big patch of sky. And the name of the game here is we're trying to understand the fluctuations in the background, so we don't care about stars and galaxies that are between us and reionization. So what we have to do is mask them as deeply as we possibly can from the image. So there you go. You've done that. This is about as deep as we can mask and still retain enough information to be useful. And then you ask, in the bits I've kept, what are the fluctuations doing? And that's an image of that. So when we take this image, and we actually don't do it in image space, we do it in Fourier space, and it's complicated. But basically, when you take these images and you ask how correlated are they between the two cyberbands, you find they're completely correlated. And then you further ask, are they correlated with Spitzer 3.6, which did this measurement at a slightly longer wavelength with different systematics? They're completely correlated with that. So because Cyber and Spitzer didn't collude in our different experiments and all that, you can be sure that whatever we're measuring is on the sky. It's not something in the instrument that's messing us up. So then you say, okay, well, can it be some local form of elation? Can it be zodiacal light, which is the fact that the Earth is in a dust cloud, which sunlight gets reflected back? So you have to say, okay, what's my estimate for how bright that can be and extract it? Same for diffuse galactic light, which is essentially that the galaxy is a reservoir of gas and dust that reflects the radiation field back to us. So that looks like some diffuse emission. So you have to limit that. And then you have to account for the residual stars and galaxies you weren't able to mask because you can't go infinitely deep, and you make estimates for how much that is. Once you've done all that, you can make a plot like this, where this is the residual at large angles compared to, accounting for all these components, which are down here. And these are Spitzer points. This is a CAR, a Japanese space telescope. This is Cyber. So the thing you notice, you guys haven't stared at this for years like I have, but the thing you notice when you have stared at it is that this residual signal is very bright. These are huge fluctuations, especially compared to, for example, Spitzer, and very blue. That is, this is the Rayleigh-Jeans spectrum, so whatever it's doing, it's going up very steeply, which is a very big surprise. So you can tell two things from this plot. One, that the reionization will have a hard time making that bright a fluctuation. You just can't put that many photons in the universe. And two, this isn't following what I just said. I just said we had two colors. We have one here that's supposed to measure one side of this break feature, and one that's supposed to be down here because it's measuring the other side of the break feature. So we look at that, and we scratched our heads for a couple years and said, what the heck is going on? So then we said, okay, well, people have proposed a variety of different models to explain these fluctuations, which have been measured for a while and not understood. We said, let's compare against that. And the thing that we found matched the data the best is an intrahalo light interpretation. So this is the idea that over cosmic time, galaxies are merging and banging together and making bigger and bigger systems. And that's a sloppy process. You lose material, you lose gas and stars in that process. And those stars go out in a big diffuse halo around galaxies, which we've known about. We've known about halo components to galaxies forever and ever. So what Cyber is doing effectively is measuring the fluctuations in those black spaces in between galaxies, which are faint, and then masking out the galaxies and looking at what fluctuations are left. And the surprising result is those fluctuations we're measuring seem to be so bright that they would imply an IHL component that's equal to all the light in galaxies in the universe, which is hard to stomach unless you think that there are a lot of faint galaxies. So this goes back to this baryon content of the universe issue. How much of the cosmos is wrapped up into stars that are flung out of galaxies? How much is in diffuse galaxies that look like small fluctuating things that we can't individually measure? Could be a lot of it that's not theoretically discarded. So this measurement, if you take it at face value, is requiring a significant new component from an unknown population. And this is an example of a serendipitous discovery. We put it into science. This is an image from the News and Reviews by Harvey Moseley, just showing the CMB, and then slices trying to illustrate this IHL model. And we originally tried to go measure reionization. We discovered something completely different, and that's a testament to the fact that this is a new field. We're kind of cowboys out here, just doing things that people haven't thought to do before. They never thought to measure this. Okay, so let's do another example. The question we're trying to ask is, how are galaxies connected to the cosmic web, and how can I trace out the dark matter distribution from them? And more specifically, what's the connection between submillimeter galaxies, which are galaxies that are bright basically 3 billion years after the Big Bang, so significantly, this is archaeology, this is a long time ago. How do the submillimeter galaxies at that epoch relate to dark matter? So the question here is, here's the cosmic web, and we're asking, what's the structure of this thing statistically? We couch that in halo terms. So one halo means galaxies that share a node, and two halo means nodes that are not connected, and you can measure the statistics of that, and via this model interpret what must be the underlying background here. So to do that, we used the Herschel Observatory, which was in space, and specifically the Spire 3-band camera, which is really a mapping machine. It can go out and make almost noise-free maps very quickly, which is exactly what intensity mapping wants. So you go and do that. This is such a map, 3 colors, 3.6 degrees on the side, and Spire made many such maps. Here's the full moon for comparison. So this is a huge swathe of sky. So you ask, what are the Fourier components that explain this image? And you make a plot like this. And then here's the data, and what you can do is you can fit models that are the 1 halo term and the 2 halo term. And what that lets you do is these models have different parameters, and these different parameters are related to astrophysics. How big is a galaxy, in terms of mass? How far apart are they? When do they form? What's the redshift current? All these complicated things. So from these models, you can infer what must have been the galaxy, what the history of this is. And from this, we're inferring that the submillimeter background, this is just one factoid from the study, is produced by galaxies with the same mass as the Milky Way, but 3 billion years after the Big Bang. So it must be that because things get more massive over cosmic time, whatever this thing turned into, we think massive elliptical galaxies, whatever this thing turned into can't be like a Milky Way, because it was that massive back then. So this is a different population we're probing. You had a question?
I'll wait till the end.
Okay, fair enough. Thanks. Okay, so those are 2 examples of a handful that exist of how intensity mapping methods can be used and have produced results. You'll notice none of the publication numbers that I showed you was before 2013, which is telling. Let me tell you about some future stuff that I'm in leadership positions in that are really exciting. Cyber 2. So the question is, how do you improve on Cyber 1? Cyber 1 was great and close to my heart, but it was not the definitive machine for this sort of thing. So how do you improve on Cyber 1? Well, you get a larger aperture and a larger field of view, or as large a field of view as you can. So you maximize the product of those 2. One thing we struggled with Cyber 1 was the detectors. The detector noise in the Hawaii 1s we were using was truly horrible and caused a lot of grief. So by going to next generation, more capable detectors where we can start to do fancy things with the noise, we're going to get better noise properties, and our heartburn from understanding the detectors will go down. And finally, more colors will allow us to trace the behavior of the intrahalo light. And that's important because what we actually want to do is reionization still. We think this method has legs for that. So, the IHL is up here and flat. So in Cyber 2, you have 6 colors now. And the idea is that you can account for this flat thing, and then you can start getting down to, at least sensitivity-wise, you can start getting down to redshift 6, 8, 10 by looking for what's dropping out, what component is dropping out, and comparing that against models. So that's the philosophy of Cyber 2. Cyber 2 is currently being built. This is a rendering of it. We now have a primary mirror. Before, you remember, there were small little refractive telescopes. This is a reflective telescope taking up the whole skin, coupled into 3 optical chains with beam splitters, shown here. Those image onto H2RG detectors, and then again it's cooled to 77 Kelvin, and it has a side-looking star tracker, so you know where you're pointed on the sky. That'll be important in a second. And parts are showing up. These are real parts. It's not all there, so assembly's kind of happening as we get things. And these are grad students of mine, actually no, undergrad, grad student, working on detector testing. And what we're doing is we're asking, can we do referencing strategies where we look at reference pixels, dark pixels, properties of the amplifier so that we can demodulate the noise and start to get the striping that was really hurting us out. So this is an example of a chop measurement that Alicia Lance led that is showing that as we do chopping, we really hit into that noise that's hurting us. So another thing I'm leading that's interesting, especially in terms of detectors, is responding to a problem we had on Cyber 1, which is you have a rear-mounted star tracker looking out the side, and it's telling you where you're pointed on the sky. And then you know the angle to where you're looking, so you can back out where you're actually looking. But what happens is, let me do it this way so you can see. What happens is as you go on ascent, which is at Mach 12 or something like that, the skin gets flash heated to 450 Kelvin. So this thing skews because of mechanical stresses. And that's fine, because I only care where I'm pointed, not really absolutely. What happens is, in your space, you radiatively cool. So now this guy's slowly coming back and introducing a drift, even though this is keeping station. So if you ask, okay, how big is that? Here it is walking across the image in one of the Cyber 1. This is a bright star in one of the Cyber 1 frames. And in general, it's smallish, but you can get it bad. This is 20 arc seconds, which is much bigger than a pixel. And it starts to make the analysis we have to do very complicated and hard. So we really want to get rid of this if we can. So that means we want a co-looking star tracker at 77 Kelvin that can tell us where we're looking on the sky. The challenge here is CCDs don't work at cryogenic temperatures because electron mobility goes to 0. So what do? Well, CMOS don't have that problem, or at least they don't have that problem in a way that would obviously preclude you from using them. So what we did was entered into collaboration that I'm leading with Goddard to get a previously used star tracker camera, which has a CMOS device in it, in a test bed, which we're testing, and we're showing the responsivity here as a function of temperature down here. It varies a little bit, but it's not changing, and it certainly says we're still seeing photons down to 70 Kelvin. And here's the noise. It's increasing a little bit. And the idea here is that we're coupling this thing onto a giant telescope, well, relatively giant, this big, telescope. And this thing's sensitive. So what we're going to propose to do, we think, is propose to NASA as a technology development program to make them a cryogenic star tracker with this technology. Okay, let me rush through. Tomographic intensity mapping is the idea not just to do this measurement in broadbands, but if we can make an image-sliced measurement. So now we're doing a map of the sky, but in small spectral bins. So as we walk up, there it is. You can measure that structure. You can ask, how's that structure correlated through cosmic time? What's happening to it? And on that, using that method, we're doing the tomographic ionized carbon mapping experiment. Time, the idea here is that ionized carbon is an excellent tracer of star formation, and it has the feature it's tracing total luminosity. So I don't have to measure individual sources here. I'm not going and using ALMA and trying to detect some piddly little line. I'm saying all the photons in this redshift slice that were emitted, I'm going to try and detect those. So what you do is you get your sky. This is a simulated sky at this redshift. And again, you're asking, what are the statistics of this image? So we use a cooling line that's in the terahertz and redshifted to the hundreds of gigahertz today to spatially trace the star formation signal. So what does this look like? It's something we're designing right now. It's a grading spectrometer, so you get a grading arc, and your detectors are here, and it's coupled to a feed horn. You get a bunch of them, so you stack them up like a toaster. And then that makes a linear array on the sky. You put all that in a cryostat, and then you find yourself a nice big telescope. In this case, this is the JCMT on Mauna Kea. And the idea is we take this cryostat, we put it on there, and then we get a couple months of time to do this survey. And we think that with that, we should be able to detect this line at redshift 7 to a signal to noise 10. That's not very impressive. So what we actually want to do, and the reason we've taken this approach, is a real experiment where we're actually doing kind of spatial imaging, or at least Fourier spatial imaging. And the idea here is this full-time experiment, and that's going to use on-chip spectrometers to feed about 20,000 TS bolometers. And the reason we didn't propose that right away is that this is a new method, and people will laugh at us if we ask for that much money. So what we want to do is detect a signal, and then say, now we want to measure it spatially. And then, importantly for this science, because 21 centimeter during ionization is tracing the neutral medium, and carbon is tracing the ionized medium, these things should be perfectly anti-correlated, and you can actually really start, in a systematic free way, which is the key, start tracing out what must be the history of star formation at redshift 10. And carbon is tracing the ionized medium, these things should be perfectly anti-correlated, and you can actually really start, in a systematic free way, which is the key, start tracing out what must be the history of star formation at redshift 10. That's very exciting stuff. Well, for me at least. Okay, so that's a millimeter wave experiment. Let me tell you about the near IR. So is near IR tomography possible? Well, I showed you that Airglow movie that was going by where it's 1,000,000 times brighter than what you're looking for. That's hard, but that stuff is all happening in discrete lines. And in between the discrete lines, you're getting continuum. So you might be able to do it from the ground, but really you want to, and I'm leading these projects to do it from the ground, but really you want to do it in space, so you have a in-orbit spectrometer, broad spectral coverage, and wide field imaging. You get access to a bunch of lines, so you can start tracing structure different ways. And the point here is this is a figure of merit. You have Cyber down here, Cyber 2 is this, Spitzer's up here. The proposed thing is in red, and it beats everybody. It's really a machine for this. But it ends up, if you build this machine, it's actually good at other stuff. Here's its specs. You get 1.4 billion galaxies in this survey, of which you get redshifts better than 3% and 120 million of them. You're mapping almost every galaxy. It's crazy. With redshifts. You get 1.5 million quasars with redshift. You get 25,000 galaxy clusters. And you get basically every galactic source. This is definitive in terms of near-infrared survey. So we proposed this to the SMEX call last autumn, and we're very optimistic that we're going to get it. I'm the lead instrument scientist. Okay, so just going really quickly, let me show you a research plan. I've divided it into 3 topics here. Just to run down, I'm grouping in red family sort of related things. Cyber 2 is happening now. Integrated test flight will be 2017, we think, the first bit of 2017. And then we go through an analysis, refurbishment, flight cycle for about 4 flights worth. Dome and land, which I didn't have a chance to tell you about, but these are the things from the ground that are trying to do this holography experiment in the optical and near-infrared. That was related to that camera I showed you on the piggybacking on the telescope earlier. Those are things that are being proposed now with build and field in a couple of years' time, and then land is slightly harder, so that's a bit delayed. Spherics, if it's selected, goes into phase A later this year, and then we start our real build in 2017. Time pilot is actually fairly complicated, so design now, build soon, with engineering in 2018. And then we'll refurbish it and try to analyze the data, understand and field it again through real science, and then at the same time work on full-time. There's technology development here that's happening, proposed design and so on. Let me skip those 2, you can ask me about them. And then data analysis, Cyber 1, which I told you about, still has data to analyze. Spire still has data to analyze, we'll be looking at that for years. And then I have just low-level data analysis, interesting little astrophysics projects that I keep going on. So what are my synergies with the Center for Detectors? Oh, that's a 10-year plan. Sorry. Here, the interesting thing here is total budget of the project in 2015 $1 million. Here's Spherics in orbit. Here's Time Pilot being a facility instrument because it's actually useful for other things, and so on. Okay, what are my synergies in case they weren't explicit for the Center of Detectors specifically? I'm an expert in testing, optimizing, and fielding new detectors. That's what I do. We have short development to deployment for new technologies. So if somebody says to me, I have a new detector, please, can we get it on the sky? We'll do it. We'll figure something out. And also because I'm involved in the suborbital community, there's opportunities for validating new technologies in flight. I think of myself, maybe I'm being complimentary here, but as kind of an expert in data analysis and specifically how to deal with near-infrared detectors with these high-fidelity on all angular scale measurements. And finally, I continue my work in the far-infrared submillimeter. This is kind of a new wavelength range for the Center for Detectors, and the idea here would be to apply the existing facilities to this new technology and try and get some synergies there. Opportunities for students, really quickly. So I'm an experimental physicist. What that means is that what I would like to continue doing during my career is cradle-to-grave involvement in small collaborations. So niche experiments saying one science case, we're going to do it, we're going to do the next thing. The idea here is that you can do that in a PhD time. So this is detector physics, electronics design, cryogenics, optomechanical, everything. This is building small telescopes, suborbital stuff, whatever, building stuff in the lab, taking it to the field, getting data, analyzing it. On that topic, data analysis, low-level data reduction, all the way through to cutting-edge cosmological science I do. And then finally, skills for the real world. In my lab, you learn laboratory physics, you learn image processing, you learn time and frequency domain analysis, you learn software, you learn firmware, you get hands-on aerospace experience. This is all in real demand by industry. So this is a big deal. And finally, at least in my career, and I'm sure in graduate students of my careers, I have had the chance to travel really cool places. Mauna Kea in Hawaii. This is Walt's flight facility. This is the South Pole. I've been there 3 times. It's really exciting. So to summarize, there's a lot of work to do at the cosmic frontier. Intensity mapping is this new wave that's really going to come on the scene in a big way. And so we have a couple results that are showing the promise of this method. And we have a bunch of stuff in the pipeline that's really going to use it to do really cool new stuff and really determine properties of the universe that we didn't have access to. Thanks.
So you showed us 4 or 5 relatively big projects that you could engage in. Are you planning to engage in all of them and not sleep, or try them all and only get funded for half and sleep?
The model is a big, not a big collaboration, but collaboration where I'm taking work packages right now, and then PIing them here, but not being the PI of the overall package, and that will change over time. But as coming in as a young guy, it's hard to PI it right out of the box. They don't give you money.
Yeah, one of your slides kind of caught my eyes, the one right before future opportunity.
Okay, there it
It's
goes.
the one where I almost interrupted you.
Yeah.
Yeah. So when I look at that graph, what comes to my mind is fractal structure.
Yeah.
When I see this, basically a power law spectrum over a number of decades. I mean, so is there anything to that?
No, that essentially is this. And I think the real question is, what are the deviations from that? And that tells us what is interesting. Because it is just a power law spectrum. And what happens is baryons effectively modify that. And so you get these kind of biases. It's not quite perfect. And you have initial conditions that reflect it. So understanding this is
Talk about
yeah.
So you mentioned that the interhalo light spectrum is flat.
Roughly, okay, we think it's flat, yeah.
Well, I was going to ask, how do you know it's flat with 2 relatively nearby?
Well, okay, so in detail it has to follow this, so I'm being a bit glib about flat, but the point is it doesn't follow organization shape. And we don't think it comes down relatively the same way, it doesn't have a break.
I have a quick question about your Cyber 2 experiment. Well, first, in this picture, it looks like you removed a lot of stars and galaxies, and you said in Cyber 2 you're going to grow your aperture larger so you can see deeper, but you're also going to get more contamination, right, from dimmer
No,
stars?
because the pixel size goes down.
Oh, okay.
That's another.
So that's how you're going to
We have
correct
a little
that.
tweak about Cyber 2 that makes it better. Yeah.
Okay.